Welcome back, everyone. It's a pleasure to introduce Vadim Vologodsky, who's going to tell us about prismatic F gauges and Fontaine-Laffaille models.
Thank you, for inviting me to speak here. So it's a pleasure. So I'm going to talk about joint work with Lepter and Duke, which he showed that describes certain those subcategory of the derived category of F gauges on smooth formal schemes over CP. Gleb is a pretty student of Bargov, so this kind of work owes its existence to hints that Bargov provided to one of us, and also a very important, also to Drinfeld, who gave us a very important okay, so I will formulate the result, and then we'll explain comments on the meaning of the various symbols that appear here. So first, so suppose I K is a perfect field. Of characteristic. And then so I look at the category of perfect prismatic gauges. That's the notation. And inside, consider full subcategory. It's a full subcategory of the triangulated category of F gauges with certain Hodge-Tate weights from 0 to p minus. So this is this. So the Hodge-Tate weights are in the city. And then the theorem is that this category is equivalent to the bounded derived category of Fontaine-Laffaille modules with similar Hodge-Tate weights. Okay. Now that's the story over a perfect field, and more generally, so suppose I have scheme X over W of K, smooth, formal. Then I can still look at the category of Fontaine-Laffaille modules. It's in this case it's defined by Faltins. And so this is an abelian category, and the claim is that it's equivalent to the category of coherent sheaves. Well, think of prismatic F gauges, but now I look at not complexes, but just coherent sheaves. The simplification of X with similar restrictions. So that's two categories are equivalent, but so in this setting, when K is a perfect field, this functor is sort of T exact. So it carries Fontaine-Laffaille modules to coherent sheaves, but it's also derived exact. So saying that so that this category is derived full inside the derived category of all F gauges. Here it's not true. And that's not true already for P1, because this category, if X is P1, it's the same as the category for the point. Right? The pullback functor happens to be an equivalence. So, well, so if X is any scheme, then this is kind of it's a too small category, right, to capture X between F gauges. So, so there is on the proof, you will see there is a generalization of lemma that Mark explained yesterday, that if you take any F gauge with this Hodge-Tate weights restriction, p-torsion F gauge, then it's automatically a vector bundle, right? So it's kind of a filtered version of the lemma that. So so this is kind of local systems, and well, we know that local systems on P1 are not particularly interesting, but the derived category with locally constant cohomology, derived category of sheaves, is something that you want to consider. So there is a derived version of this statement, but the category, kind of the derived really category of Fontaine-Laffaille modules, it's not derived of something abelian. This regulator category of Fontaine-Laffaille modules does not exist in literature, so I will just say derived. Okay, so the content. Well, now I want to say some a few things about F gauges. This category here, this category of F gauges, is kind of universal home for prismatic cohomology theory. So if I have any scheme, smooth proper scheme over W of K, it gives rise to an object theorem. And if its dimension is less than p minus 1, then it's actually belongs to this subcategory. And so an F gauge remembers this F gauge corresponding to a scheme, remembers everything about prismatic cohomology of this scheme corresponding to all prisms, together with Nygaard filtration, with the Frobenius. So informally, this result can be kind of means that it gives a procedure to recover prismatic cohomology of a scheme of small dimension from very basic, from kind of old cohomology theories like the Rham cohomology and crystalline cohomology plus various Frobenius, right? Hodge filtration. So though this procedure is not quite explicit, and here it's even more kind of complicated. So, for example, okay, so generalities on F gauges. Are there any questions? Say again? Formalismus. So this theory is due to Barkov, Chekhov, and Drinfeld. And it has the following format. So if you start with any reasonable scheme, say locally complete intersection over W of K, that's I mean it works more generally, but let's stick to this. So then so the construction assigns to such X a stack, a formal stack. And this construction is functorial, so if I have a map from, say, Y to X, then this gives me a map of stacks. And in particular, I can take the derived direct image structure a sheaf. This gives me an object. This category of f gauges on X. So this is f gauge associated to X in Y. And now this step itself is constructed in two steps. Well, I'm not telling you the construction, I'm just introducing some notation. So there is a first one defines a certain step Nygaardization of X that contains two copies of prismatization. These are open embeddings with disjoint images, and the step that we are interested in is coequalized. So this is, well, very an example. So let's take in the case when X is actually a perfect field, spectrum of a perfect field, this construction is was discovered by 1980s by Ekedal Fontaine, Janssen, okay, so first I will tell you what are sheaves on all these stacks are.
But yeah, now you have, before you had X through the W.
Yeah. So here, this is not an example.
Okay.
Yeah. So, but already for like CP, it's kind of a little, well, it's hard to, but still, it's useful to have this example in mind. So this is kind of universal home for symptomification of K, is universal home for cohomology theories of schemes over field of characteristic P, right? So this describes the linear algebra structure, crystalline homology of such schemes. So, okay, so this is, I first tell you what sheaves here are, and well, by definition, these are just complexes of filtered complexes of W of K modules. So this is W of K bit vectors, and so filtered complexes. So this is my filtration. But with the property, well, with a structure that such that this filtration is a refinement of the p-adic filtration on W of K. What it means is that we are given maths in the opposite direction, such that composition P minus P plus as well as P plus P minus is multiplication by P. So if you think for a second that this maps, this filtration is an honest filtration, these are embeddings, then the existence of this V plus just tells you that multiplication by P takes a 9 to a 9 plus to the smaller term, right? So a very important example of this picture comes from geometry, right? If you have a smooth variety over K, then the crystalline homology is equipped with a Nygaard filtration, which has this property. It's a refinement of the p-adic filtration, the sense that I just described. Okay, so that's the description of this category. And now, well, I will just tell you that this, the prismatization in this case is formal spectrum of W of k. Well, I forgot if I mentioned that all this dot must be p-complete. So everything that we consider here, p-complete. So, and I need to tell you what are the functors. So if I have a diagram like this, a gauge, then I define two W of k modulus, so plus infinity and negative infinity. I will do it at the same time. So it's going to be colimit with respect to either v plus or v minus. This is okay. So and so now I can tell you what DQC of a symptomic is. That's again, it encodes the information that crystalline cohomology. So in addition to the Nygaard filtration, you have the Frobenius. And the Frobenius can be vertex map. So you have this n v minus v plus you have an isomorphism phi from Frobenius upper star of n minus infinity to n plus infinity. Right? So that's the description of the category of F gauges over perfect field of characteristic field. And in this case, I can even tell you what the specs are. So let's so what we have here, well, this linear algebra structure can be thought as well, it's given such a linear algebra structure is equivalent to given a graded module over certain algebra. So this algebra is generated by these two variables, v minus v plus, and it's commutative. So I will just write one relation. And I'm supposed to look at the graded modules over this algebra. That means that I want to take this formal scheme and mod it out by GM, the multiplicative that acts here, such that the degree of v minus is -1, degree of v plus is +1. Okay, and now, so there are two maps. So a sin in this case is defined as follows. So you take you can call this structure. So so you have formal spectrum point, and it maps in two ways to this Nygaardization. So well, so you can consider open subset here given by equation inequality. V minus is not equal to 0. And another open subset is V plus is not equal to 0. These two open subsets do not intersect each other. So you get two open embeddings. And this each of this subset is isomorphically equivalent. Formal spectrum. Okay. So that's what I want to consider, except that because of this Frobenius twist, I need to modify it. So here this is G minus. So this is obvious embedding to the subset where minus is not equal to 0, and the other embedding I have to recompose with the Frobenius on W, which is nice. But you do the glue in infinity and minus infinity. Okay. So that's the how this picture looks in the simplest case. So in general, there is a kind of factor of points description of simplification, which is, well, it's genius and involved. But I will not tell you this description, but I will tell you kind of some points of simplification of X that I'm going to use. So
sorry, could you just say one more time where does J minus and D minus and D plus?
So take this string and invert V minus.
Okay.
And then when you take the quotient by GM, you get canonically W of K.
Okay.
Does it make sense? Or equivalently, just send it to V minus equivalent.
So you got a question.
Yeah.
So K-sin is not filtered. So how does it see the Nygaard filtration?
Say again?
So K-sin is not a filtered stat. So how does it see the Nygaard filtration in the stat? So do you pull back to K in?
Yeah. I mean, right. So by definition, K-sin is a equalizer. Of this map. So if you have a sheaf here, you can pull it back. Does it make sense? Good. So okay, so here is some maps that I'm going to use, and these maps are if you want to kind of recover prismatic cohomology corresponding to a prism from net gauge, this is the maps that you are going to use. So construction. Suppose I have any prism, and for simplicity, so delta ring. And for simplicity, I assume that the ideal, invertible ideal is defining the prism is principal, and then suppose I have any schemax together with a map from the formal p-adic spectrum of the quotient to X, then any such map gives rise to a map of stacks. So one is well, I take this prism A, I draw a hyperbola, so V minus V plus, product is V plus equal, now this time is equal to G. And then I move it out by G. And this guy maps to X Nygaard. So every map like this gives rise to a map from this hyperbola to X Nygaard. And the property, so an instance, an example of this we see in this, well, if A is a perfect field, or more generally, a perfect prism, not necessarily characteristics P, then this map is an isomorphism. But in general, it's not. It's still, well, it exists. And if you, well, again, there are two maps, J minus and J plus, defined similarly. And you can precompose one with the Frobenius, defined by the delta structure. So you get these maps. And so the property of X scene is that this, if you post-compose these two maps with the projection to X scene, then they are going to be. Okay, that's the picture that I'm going to use. And in particular, let's construct some points of simplification of the point of W of K. It's a complicated stack, but we want to kind of understand sheaves of this stack. Okay, so let's take for A, Berkisian prism, W of K. So any prism gives me a map from this formal step to prismatization to the symptomification of Z. In particular, map to X is just no structure. So in particular, well, so I can take the Berkisian prism. So D is P minus U, and Frobenius, the delta structure is determined by the requirement that it goes to the fifth power, but Frobenius lift, and then I get this have this Nygaardization, and this is just notation for stuff W of K. Okay, so I have a map from this hyperbola P minus V plus OD modulo GM to this Nygaardization. This hyperbola has two important substacks. What is substacks? One is a fine line, modulo G. This is W of K, V minus modulo G. So this, well, I need a name for this. This is A1 mod G, right? A1 is over W of K, and the map is takes V plus to 0. And there is another map that I'm going to use that takes U to 0. Yeah, so if I take send U to 0, it's going to be mapped from W of K V plus V minus. Now the product is T, and again modulo G. So we already encountered this object. This was K9. So in geometric context, if I have a scheme, any scheme X over W of K, so I get a gauge corresponding to this scheme. If I pull it back here, right, I get a sheaf on A1 mod GM, which can be thought as a filtered complex, and this is the Rham cohomology with and if I pull it back here, well, then it depends only on the reduction of my scheme modulo P, and this is the crystalline cohomology equipped with the Nygaard. Okay, so so we don't know much about W of K, but what? So there are two important maps that we have here. One map is from A1 GM, and let's call it Rham plus. So rho Rham is for the Rham realization, and plus for the Hodge filtration, right? I consider it together with the Hodge filtration, right? That's the map defined by this time. And there is a yeah, this was X. Yeah, and there is another map, which I will call rho Chris, from this K9, right? Or I think the choice of this notation is clear. Geometric interpretation of this map. Okay, so we have this map, and we also have a map from Nygaard to A1 mod GM. I will not tell you what this, so the definition of this map should be obvious from this coordinate presentation. So given a map like this is equivalent to, well, it's actually, it comes from a map of algebras, from this algebra to this algebra. That's the most obvious map, the xv minus to v minus, right? So this K Nygaard is a filtered step, so it leaves over A1 mod G. That's the reason.
Is A1 completed or is it just A1?
Completed, yeah. Thank you. Okay, so now, so we have this triangle that isn't commutative. So let's see what commutativity would mean. It means that if I have a scheme over X, I look at its Rham cohomology with its Hodge filtration, right? I view it as an object here, then I pull it back here. So algebraically, this construction does the following. So you have a filtered complex. So objects here are filtered complexes. Objects here, particle coherent sheaves here, are complexes with a filtration which is a refinement of p-adic filtration. So if you have any filtration, you can make it, there is a universal way to make it a filtration compatible with the p-adic filtration, right? And so the question is whether by this downgrading procedure, we obtain the Nygaard filtration from the Hodge filtration. Right? So, and the answer is no. It's not. So it should not be commutative. Well, we should not expect it to be commutative. I didn't tell you a definition of this, but it's kind of would be ridiculous to, if it were commutative. Because we know that it's not commutative in general. However, so there is a small modification of this, which makes this diagram commutative. So to explain this, let's introduce a ring B. It will be, it will contain, it will be a subring of W of K, V plus A minus, product is B. So I take this ring, and I tensor it with Q. So I got P. And so B is generated, is defined as a it's WK algebra, subalgebra. Generated by V minus and V plus to the N over N. Very good. So another way of seeing this algebra is the following. So you can take B.
Excuse me, it's a definition?
It's a definition, right? Definition. So here is another definition. Take W of K and consider the ideal generated by, and take its divided powers, right? This stands for the divided powers. Powers of the ideal. And take the resource. So it's a filtered algebra and apply the risk construction. So by definition, graded, so that's a graded module. This is a graded algebra, right? It still has the same, well, it's grading is induced by the grading here. So in graded modulus over this algebra, so that's another definition. And so by this description, it follows that graded B modules are.
Does it say P?
What?
In this definition, you took divided powers. That's the box.
Yes, that's. I take W of K and the divided powers of this ideal generated by.
But like if P is bigger than 2,
Yes,
it already has divided powers.
no, I mean, yeah, but it's a subgroup of W of K. Okay, so let's say N is equal to minimum of orders of P to the M over M factorial, where M is greater than N. Then divided power of this ideal is just the ideal generated by this.
Absolutely larger than P, smaller than.
Maybe
Right.
I'm just confused by the notation.
Yeah.
What does box dot?
Well, if you have a divided power ring,
Yeah.
so if you have a ring with an ideal and you have divided powers on this ideal,
Yeah.
you can take the divided powers of this ideal, right?
Okay.
Yeah. So for example, it contains element P to the N over N factorial.
Right.
But it contains more elements. It contains P to the M over M factorial, where M is any number greater or equal than it.
Okay.
Right? And I take the ideal generated by all this.
Okay.
Does it make sense?
But I'm still confused why it has to do with the previous definition.
Well,
Because there it looks like you have this V plus as an extra variable. And in the end, it should be like related to something like U minus P, right?
yeah, but
V plus is given by multiplication.
well, but what do you do in this construction? So you take the direct sum of all terms of the filtration. So if you so just you can do the computation and see that if you look at the so this is a graded algebra. If you compute so B is B direct sum of BI. And what are BI? So I claim that as a WK module, this has rank 1. And it's generated either by power of V minus in degrees less than 0, or by V plus to the I over something, over some integer. Okay, so this P it contains, so it definitely contains this algebra. So there is a map from any questions? From this quotient, and also map like this, which is just a composition. So now lemma, which is due to Drinfeld, we learned it from Drinfeld. Is that the diagram is confused. I mean, this diagram.
Anything to do with the only theorem of measure on F gauges?
Oh yeah, definitely.
And what the maps are.
What?
Just say what the maps are at the top.
Okay, so K. What is the definition of K Nygaard? You take spectrum of this algebra and mod it out by GM. But B contains this algebra, right? So this gives me this map. And this map is defined as the composition with the dot.
Okay.
Okay. So in geometric context, this is a well-known fact, and it's just the statement that, well, so if you have a scheme over K, you have its crystalline homology, and there is something called the crystalline Hodge filtration. And this crystalline Hodge filtration can be obtained by downgrading the Nygaard filtration, and also if your scheme comes with a lift over W of K, then it can be obtained as a downgrading of the Hodge filtration, right, which is over W of K. So, and this crystalline Hodge filtration has the property that it's a refinement of this divided power filtration on W of K, right? So it's actually this crystalline Hodge filtration can be viewed as a module, graded module. And the commutativity of this diagram in this geometric context is amounts to the statement that I just explained.
If instead of taking the W of K there, if you took the algebra that you get from W of K by freely adjoining divided powers on P, maybe not the usual divided powers, and took the Riesz algebra of that, would the diagram still?
Commutative. I mean, well, I think that this algebra here, this stack here, is the fiber product of this diagram. So I'm not sure whether it implies. So what is the? What does it say about question? But it should say something. Okay, so now I can describe for you this functor in one direction. Yeah, maybe before I do this, so here is a corollary. So corollary. Yeah. So yeah, first, even before corollary, I need to introduce annotation. So annotation. So I will want to tell you, recall for you what are Hodge-Tate fields. I will do it just in this case. So I get, so this is a full subcategory of gauges on K. So it consists of this modules and minus plus one with the following property that some maps are isomorphism. So well, B is here. Yeah, so n a minus one. All these maps are isomorphism starting with degree A, and also all maps n B. The direction also isomorphisms. Okay. So and now, so if I see a F gauge, so for example, the shape here, I will say that its Hodge-Tate weights are in this interval if it's pullback. Okay, Nygaard, same property, and also if I have a gauge on W of K, well, its weights are defined using this pullback. And so here is a corollary of this Drinfeld and Bhatt. So, and to state it, I need a name for this map. And I will call it, this is the Rham. And the corollary is the following, that if I start with any gauge with weights 0, p minus 1, W. Then, so I can do two things. I can pull it back and look at its crystalline realization. And on the other hand, I can, it comes with a Nygaard filtration, or I can look at its Rham realization, its Hodge filtration, and then I can downgrade the filtration. Right, one is this T function. So I want to apply everything to it. The claim is that I get a nice price. So although this diagram is not commutative, this triangle is not commutative. For objects of small Hodge-Tate weights, it behaves as it were. And the reason behind this is that so there is a map from this algebra to B, and it is an isomorphism in small degrees, in degrees greater than and smaller than. Okay. So now I can explain for you at least the construction of this this functor here.
P minus 1.
Yeah, p minus 1.
But in classical Fontaine-Laffaille theory, isn't that like if you go all the way up to p minus 1, that it becomes a little bit delicate? The second.
Yeah. So.
Okay. But the corollary is okay.
I will construct a functor for you in the range from 0 to p minus 1. So construction of functor. So I need to tell you what are the, sorry, I need to tell you what, before I construct the functor for you, I need to tell you what this category is, right? Fontaine-Laffaille modules. So, okay, so here is the definition. I will leave it to for you to compare it with a classical more, well, definition of Fontaine-Laffaille. It's very close to this. So I just consider I will define derived category for big Fontaine-Laffaille modules. It contains as a full subcategory the category this bounded derived category here. And this is just consists of the following pieces of. So it's a sheaf M on A1 mod G. Together with an isomorphism. Well, if I have a sheaf, I can take its fiber at point V minus. V minus is my coordinate on A1. And I can also take a fiber at V minus equal 1. And what I want is an isomorphism. This is so. So sorry, it's not a. Of course, it's not a property. It's a structure. So I consider the category whose objects are classically given sheaves on the affine line, together with an isomorphism between the two fibers, up to Frobenius.
We can you repeat the two fibers here? We can.
Fibers are at point.
I cannot read them.
Yeah. So one fiber is, so I have A1 and I have B minus equal P and B minus equal 1. So I identify the two fibers.
But on the left you have Frobenius Probak and
Frobenius Probak. On the right I don't have.
No Frobenius.
F is M.
Oh yes, sorry. Sure. Yeah. Does it make sense?
And there's the claim that
I mean, you also have an appealing character.
So if I replace this symbol GQC by coherent sheaves, if I consider coherent sheaves on a one mod GM, that's equivalent to Fontaine-Laffaille definition. And this is an abelian category by Swag. Well, it's slightly non-trivial. This requires a proof that any coherent sheaf on A1 mod GM with such an identification is automatically a vector. It's again similar to Mars.
In this definition,
Sorry, it's if it's split torsion, then it's like otherwise. Yeah.
excuse me, Vadim, in this definition, where is hidden the p-divisibility of the F-iteration?
So what? Okay, so I'm looking at objects here as filtered complexes. F0, F1, F2, F3, and so on. And then I claim that just given a map from this Frobenius pullback is equivalent to given a map collection of maps, semi-linear maps from F0, from F1, but the diagram is not sort of, this is not commutative. It's, I mean, this is phi, and this is phi over p, and this is phi over p squared, and so on. So given a sheaf on A1 mod GM, together with a map between the fiber over A minus equal p to the fiber at 1, is equivalent to given a filtered complex together with maps like this. And if you want it to be an isomorphism, then you need to Fontaine-Laffaille condition. Okay. So now my goal is to, starting with an F gauge, I'm going to produce for you an object of this category. And so let's see how it works. So what I'm going to use is this corollary of lemma. So I might be able to say use its lemma to there is something about the like p-adic Cartier transform sort of p-adic Simpson correspondence, not in the sense that well function sense, but there is a easier another version of p-adic Simpson correspondence, which is much font. Alain mentioned actually this work of and that's an issue. Yeah, so we'll see how this diagram gives rise to Lexington function. Okay, so very good. So now I want to tell you how to construct this functor, and this will be functor from GPC p minus 1 of W of k to big category of Fontaine-Laffaille modules. Sorry, not consider gauge, all gauges not necessarily perfect. And there is also similar distinction here. So the ingredients that we are going to use, we are going to look at this diagram. And so the consequence is corollary. There's that if you work with sheaves and this small Hodge-Tate weights, so this triangle, the lower triangle, behaves as if we are commutative, and that will be important for us. So, so let's see what we want to follow. First of all, so suppose I have an object here. Okay. I need to produce for you. I need to produce for you this. Well, so I have W of k, Nygaard, and I have W of k C. First thing that I can do, I can pull it back. So this will be y. I can pull it back, and then I can apply order to its pullback. Right. So I get a shift on A1, 1G. Now I can have to explain for you how to identify the two fibers, right? This comes as follows. So so I have K sin is Nygaard. Right, and so here I have here I have V1 more GM. And there is a map here which I call T. And so recall that this stack here is obtained by gluing 2 points, 2 open points in this K Nygaard. So this was J plus composed with the Frobenius and J minus. So if you compose these two maps with this map, right, that takes, well, it was something very explicit. It's on functions, it takes V minus to V minus. So here one map is given by equation V minus equal 1, the other is V minus equal 2. So that means that this composition here, these two maps here, one is V minus equal 1, the other is V minus equal 2, right? So I start with a gauge here, I pull it back this way. And then I want to show that construct an isomorphism between the two fibers, right? I want to pull it back with respect to the one map and the other. But so if I write each of this map as this composition, then we can describe the so we are going to use that if I take T upper star of M, then this is rho Chris of so, but this rho Chris, well, it's actually, it comes from this F gauge of an F scene. So the two fibers are identified. So this gives me maybe it's affiliation between and okay, and that's my phi. Does it make sense? So what I'm using is that if I start an F gauge, is an F gauge, I pull it back on these two maps, then the two fibers, the two restrictions are canonically identified. That's by definition. On the other hand, the gauge here can be obtained from this M by pulling back along T. And this is the key step. That's treated stuff.
I'm confused. It looks like you use the triangle as commutative.
Yes, it's not commutative, but for objects of small Hodge-Tate weights, it behaves as a commutative, right? Does it make sense? Okay, so I have 2 minutes, and I will tell you this maybe 1 minute. What kind of ingredients in the proof? Well, I mean, the claim is that this functor is that I define here is not an equivalence, but it is an equivalence if you restrict weights slightly smaller, right? The integral makes slightly smaller. So that, well, it's a functor between some complete differential, well, infinity case, stable infinity case. So in order to show that it's an equivalence in range 0p minus 2, it suffices to show that it's an equivalence on FP module in both cases. So you consider sort of here, you consider sheaves on W of k, seen tensor FP. And here you consider, well, similar category, but it's, well, you just replace A1 mod GM over W of k by A1 over the residue. So you want to understand gauges here, F gauges. And so there are 2 ingredients. So one ingredient is, so this step, there is a U substep, which is given by, it's a 0 locus of, it's on the one hand, it's really a reduced locus. So this is a kind of, you should think of this as a formal step. It's the original stack was formal in 2 directions. It's still formal. So there is a, this guy is a formal kind of neighborhood of its reduced locus. And this reduced locus is given by one equation, locally, by one equation, which is called V minus. Sorry, V1. It's a section of a line bond, which is non-zero divisor. And sheaves here can be understood very explicitly thanks to well, Drinfeld described this step quite explicitly. And so it turns out that if you look at DQC of W of T reduced with this Hodge-Tate then this category is equivalent to Fontaine-Laffaille modules, but with derived category of Fontaine-Laffaille modules standard 0 p minus 1 W of T. But you tensor this category with sorry, it's FP. So here are the Hodge-Tate weights are from 0 to p minus 1. And it follows from, well, it's a result of explicit description of this step. And the second assertion, which this is where Bargov helps us a lot, and it is also kind of, it's a result of computation by Bargov and Jacob. So the restriction functor is an equivalence on quasi-coherent sheaves in Hodge-Tate weights from 0 to p minus 2. So if you look at DQC W of T, that's the FP. Of W of T reduced. And this is an equivalence in weights from 0 to p minus 1. Okay, that's all I got.
Sorry, could you say something about how you get between this like Fontaine-Laffaille modules and like these big Fontaine-Laffaille modules? I'm a little confused about.
Yeah, one is the full subcategory of the other, and and you can describe it. Yeah, so you can consider big Fontaine-Laffaille modules and look at the complexes that have only finitely many cohomology sheaves, and all these cohomology sheaves are.
I think somehow you mentioned like for this Fontaine-Laffaille modular, if it's coherent.
Say it again.
So for this coherent Fontaine-Laffaille modular, if it's p-Gaussian free, and then you start is always a matter bundle.
Yes.
There are similar things for coherent shapes or with string symptomic.
Yes. So if you in this Hodge-Tate trace, if you take any coherent sheaf here, which is p-torsion, it's automatically a vector bundle on the corresponding stack.
Does that follows from the thing you mentioned?
Say again?
Does that follow from the thing you mentioned about Fontaine-Laffaille modular, or you just prove it?
Well, it's rather, I think it's a sort of, it's a consequence of the proof rather than of the statement. Yeah.
What is the definition of the map T?
T. So this is defined as a quotient. Well, it's a projection of a hyperbola to x-axis. Yeah. So this was defined as a spectrum of some algebra, W of k, v minus, v plus sp. And this was T. This was definition of this is the algebra that was used to define k Nygaard. And here we have algebra W of k v minus. And I claim that that is a so this map T is induced by a map of particles that takes v minus to v minus.
Can anything be said using this method about higher weights?
I don't. Well, I am still hoping that something can be said about this category, right? When weights are not from 0 to p minus 1 to p minus 2, but well, this range. So Jacobson has some ideas. However, I mean, it's easy to give to explain what goes wrong. So it's there is a map in the category this category from FP to FP twisted by p minus 1. This map is called V, has a name, V1. And this map, if you apply the functor to Fontaine-Laffaille modules, it becomes 0. Because there are no maps between this Fontaine-Laffaille. This accidentally, this is also an example, first example, where the entire realization fails to be fully faithful. But for different reasons, this map becomes an isomorphism. Little Fermat theorem is p minus twist is the same as p asymptotic sheaf. So it's yeah, and it's an isomorphism. So under one functor, this map becomes 0, and the other becomes an isomorphism. So, but I don't know. I mean, I hope that one can still understand something.
You explained an explicit description of the Nygaardization of K and of the quasi-coherent derived category thereof. Is there also a similar description for the Nygaardization of the bit vectors of K?
Well, it's not. I don't know what means similar. No, probably the answer is I don't know. So I don't know of any kind of simple description which would be.
Okay, thank you.
I mean, it's defined by some explicit equations as a motion of something by groupoid or maybe even by a group. But this kind of equations are as complicated as multiplication in the ring of vectors or addition, and there are usually infinitely many equations. So it's also given kind of quite explicitly, but too many equations and they're too complicated.
Thank you.
Okay, thank you very much.